Welcome to You Got Hope Chemistry. I'm Hope, and you're about to learn some chemistry. In today's lesson, we are going to look at the difference between a monoprotic and polyprotic acid and base, as well as how they react in water, or essentially an ionization reaction. Now, we have looked at some of these already, so I'm going to do a little bit of review of what acid ionization looks like in water. And then we will do a number of examples talking about monoprotic and diprotic, triprotic acids and bases along the way. So the first thing I want to talk about is what is an ionization of an acid in water. An ionization of an acid in water is essentially when an acid is reacting with water. If it was a strong acid, it would go react completely with water to turn into its conjugate base and hydronium. So what you would have is your acid molecule as one of your reactants, and then it's always reacting with water to produce what we call a conjugate base, which is essentially just the same thing as the acid but one less hydrogen ion, and hydronium. So the reason why I have just left these spaces here is because we're going to get in the habit of writing out our equations in this pattern, so it becomes easier to understand. If I had a weak acid, it's the same thing. You would have your acid, it would react with water, but not to completion. And so what I would do is I'd use an equilibrium arrow, and it would turn into its conjugate base plus H3O plus aqueous. So again, this would be my acid, and this would be my conjugate base, which essentially is just one less hydrogen ion. Now the term conjugate base doesn't apply to our course at this point. It will apply to Chemistry 30. So I'm just going to introduce it, but I would never ask you what is the conjugate base of a certain acid, even though you could look it up right in your data book in the acid and base chart. So let's start by doing these things, writing out reactions like this, one for an acid, strong acid and one for a weak acid, based on our examples down here for a monoprotic acid. So first of all, we need to discuss what monoprotic means. So mono simply just means one. And the protic part is basically talking about the proton. So this has one proton in it to ionize. So monoprotic means one hydrogen ion acid. So a monoprotic acid has only one hydrogen atom per molecule that ionizes. So generally what you're looking for is something that has a single hydrogen to start, like an HCl, HBr, HI, HF, HNO3, HClO, something like that, where you only have one hydrogen to start and it's aqueous, and of course it can ionize. Or you're looking for, if it's an organic acid, a carboxylic acid, one COOH group. Only this H on the very end ionizes, not the ones that are beside this carbon here. And this is due to the fact that these three hydrogens are in nonpolar bonds with this carbon, and water doesn't have the ability to strip those hydrogens off of the carbon due to the fact it is a nonpolar bond. Whereas if you have a COOH group, which looks like this H here, which is red, is this H here, and this is a very polar bond. So if a water molecule comes by this carboxylic group, essentially what happens is the hydrogen will leave the carboxylic group and join the water molecule to form hydronium. So just keep in mind that whether it's monoprotic or diprotic, which means it has two protons, or triprotic, which means it has three protons to donate, you have to have that many COOH groups. So because I only have one COOH group or carboxylic group, it can only ionize once. So let's say the question is to write the ionization equation for HCl or write the ionization equation for vinegar, which is CH3COOH. What I'm going to do to get into the habit of writing out a correct reaction is I'm simply going to use these blank spaces plus water, and I'm just going to add the parts in that are new. So again, HCl is a strong acid and vinegar is a weak acid. So I'm going to write out two equations, one for HCl and one for vinegar. So I'm going to just go blank plus water, a single arrow forward for HCl because it's a strong acid, so this is 100% forward, blank plus H3O plus aqueous. Now, all I need to do is take my molecule of HCl, so HCl, and put it into that blank. Now, as a review, this H ends up getting donated to this water like this. So when I want to figure out what goes in the blank on the right-hand side, on the product side, I kind of just have to look at the molecule and ask myself, well, how has this changed? Well, it's lost the H, so the only thing left there is Cl. And it's also lost a positive because this was a proton, so now it's negative. So the HCl turned into its conjugate base, which is Cl minus, because it lost one proton, so that's one hydrogen less and one positive less, making it a negative. Essentially, it's just turning into its anion. The extra H went to the water and has become part of hydronium. So water has gained an H, so it's gone from 2 H's to 3 H's. And it's also gained a positive because, again, a proton is positive, and so it has become positive. If I was to do the equation for vinegar, same kind of idea. I just go blank plus water. And then I have an equilibrium arrow because this reaction doesn't go 100% forward. It actually goes both directions. The reactants react with each other to make products. The products react with each other to reform the reactants at an equal rate. Blank plus hydronium. And now all I have to do is just fill in those blanks. So if I'm starting with vinegar, it's CH3COOH. Now we learned that the H that's lost is on the end of the COOH group. So what's left? I have CH3COO minus. So again, this would be the acid. This hydrogen would be donated to the water, but only in a small percentage because this is weak. And this would produce what we would call the conjugate base. Again, that's a term that I'm introducing to you, but you don't really need to know, which has one less hydrogen. This hydrogen is gone, so it's missing that hydrogen. And it's also lost a positive, so now it has become slightly negative. And again, as a quick review, the water has gained a hydrogen, so it's gone from 2 hydrogens to 3. But that hydrogen is a proton and it's positively charged, so it's gone from no charge on water to a positive charge on hydronium. Now, another way that you can write an ionization equation, or essentially the reaction of an acid with water to produce its conjugate and hydronium, is to go to your acids and bases table, and you can do the following to help yourself out. So I'm going to do the same two examples of hydrochloric acid and vinegar. So I found hydrochloric acid. Here's its acid. So this is my blank. And then I would go plus H2O liquid, single arrow forward. This would be my blank. So if I have trouble figuring out what the product is, I could actually look it up in this table. And then plus H3O plus aqueous. So that's the exact same ionization equation we wrote in our notes. But if I'm getting stuck and I need help, this is a way that I could solve for what goes in those blanks. It's always blank plus water creates blank plus H3O plus. So I'm going to scroll down and we're going to go to vinegar. Same idea. So I know I'm dealing with vinegar, so I go blank input vinegar plus H2O liquid. Now I need an equilibrium arrow because it's weak. Blank plus H3O plus. And now I can see, oh, it's the H on the end that has ionized, and now I have a negative charge. So you've got to remember that every time you lose a proton, the species becomes one more negative. So if you look here, this started as being one negative and it's turning two negative. Or this has no charge and it's becoming one negative. Or this has a two negative charge and it's becoming three negative. As an acid, you're always going to add a negative charge to the product that is being produced. The next thing we're going to look at is polyprotic acids. And so polyprotic acids, there are two different types. Okay, so you have diprotic and you have triprotic. Now, the majority of the time, people just use the term polyprotic. Of course, the term poly just means more than one, whereas di is very specific, it's two, and tri is very specific, it is three. So a diprotic acid has two hydrogens to ionize. And so if you look at this example here, this is H2, both of those could ionize. And on the other side, I have two COOH groups. And so on the end, you each have a hydrogen which can ionize. Those are two different carboxylic groups attached together by the C's at the C point, okay? So I'm just going to show how this would happen using H2SO3. So again, what I want to do is I just want to start with blank plus H2O liquid is in equilibrium with blank plus hydronium. I know this is a weak acid, but I have to do this twice because it's going to do it once for one hydrogen and then it's going to do it once for the next hydrogen. So blank plus H2O liquid is in equilibrium with blank plus H3O plus aqueous. So we'll start with the H2SO3 first. And what it's going to do is it's going to ionize or react, and it's going to donate this hydrogen first. Okay, so H2SO3. And then it's going to be, of course, have one less hydrogen. So now we're HSO3. We have one less hydrogen because we've lost one to the water. And we also lost a positive, which is going to make this negative. So remember, if you're an acid and you start with no charge, it's going to end up becoming one negative. Okay, then what I would do is take this product and bring it down here. So I'm starting with HSO3 minus. Now this hydrogen now can get donated. So now what's left of HSO3 minus is, of course, SO3 because it's lost the hydrogen. And if it was 1 minus, it has to become one more negative. So now this is going to be 2 minus. And of course, both of these are aqueous. Now, I'm going to clarify a couple of things that aren't really super important at this point, but this first reaction doesn't happen a whole lot because H2SO3 isn't a very strong weak acid. But the second step is even worse. So let's say I'm going to make up a number. If this was something like 5% ionization, this one down here would be 0.05%. It would be a lot less. And again, those aren't exact values. I'm just making them up. But that's how forward this would go. Maybe 5% of the H2SO3 would react, and then here about 0.05% would react with water. So this happens less on each step that we do. Now, if I was to do a triprotic acid, of course, I would have to have 3 H's, or I would need to have 3 COOH's. So for instance, I would have to go blank plus water is in equilibrium with blank plus hydronium. And then I'd have to go blank plus water is going to become blank plus hydronium. And then next, blank plus water is in equilibrium with blank plus hydronium. So there's not a lot of triprotic acids out there. Phosphoric acid is probably the most common. This very complex looking organic acid is citric acid, which you probably take in almost daily in a lot of drinks that are out there or in fruits especially. So all I would do is I'd start with, H3PO4. and then I'd lose an H, so now I'm H2PO4, and then of course I have to add a negative. Then I would take that answer and I bring it down, so H2PO4 minus, I remove an H, HPO4, and then I have to add another negative charge, 2 negative. And then I have HPO4 minus, and then I remove one H, and 2 minus, and then I have to remove an H, so now I'm PO4, and of course I have one more minus, so now I am 3 minus. So there's 3 different steps going on here. Now H3PO4 is a fairly strong weak acid. This actually happens quite readily. Still, the percentage isn't that high, okay? But each step that happens after this ionization happens less and less and less. Essentially, this one almost doesn't even happen at all, but this is how it could be seen as a triprotic acid. It can, react with water 3 times. Where it's really going to act as a triprotic acid is if I was to neutralize H3PO4 and I added to it 3 times NaOH, the hydroxide would have the ability to remove all 3 hydrogens for sure, whereas these are just showing ionizations, or the 3 possible ionizations of each hydrogen in H3PO4. So now let's look at bases, and the first thing I'm going to do is again review dissociation and ionization of a base. The first thing I want to remember to mention is only strong bases dissociate to form hydroxide ions, whereas the ionization or reaction with water is what's going to happen with weak bases. So I'll give you a couple of examples here. The first one I'm going to say is a dissociation. So for a strong base that dissociates, you're going to have some metal cation, group 1 usually, lithium, sodium, potassium, something like that, with hydroxide, and it's aqueous, and then it's simply going to turn into its cation. I'm going to call it X plus hydroxide ion. This is a dissociation. It's not a reaction with water. It already contains the hydroxide ion, which is base. And so really your X or your X plus, you're looking at things like lithium, sodium, and potassium, most likely. If you have a weak base, on the other hand, it is going to react with water. So it's going to have a similar kind of feel to it as the weak acid did. So it's going to be blank plus water. And this is going to have to be in equilibrium. And it's going to produce blank plus OH minus. That's the difference, is we're making hydroxide, not hydronium. And then all I have to do is I got to figure out what goes in this blank space. And no matter what happens in there in terms of what species it is, this water is really going to be the one that donates the H plus. So that's why the water goes from having 2 hydrogens to just 1. And that's why it goes from no charge to negative, because it's losing a positive. Now this means that this product has to be 1 more positive than the reactant, because it's gaining a hydrogen ion which is positive. So this is the exact opposite of an acid. An acid will become 1 more negative, whereas the weak base will actually become 1 more positive. So let's look at these first. So a monoprotic base is a base that's either going to dissociate or react with water, forming hydroxide ions. So I have 3 examples here. One of them is a strong base, KOH. One of them is a weak monoprotic base, which is an ion. And one is a molecular monoprotic base. So we're going to do one for each of these. I am going to start, though, with KOH. So KOH is a strong base, and it is simply going to dissociate. So we have KOH aqueous or solid, and we put it into K plus aqueous plus OH minus aqueous. And that's all it is. And this is balanced. They're always balanced 1 to 1 to 1 here. Now, the next 2, one of them is ionic, of course, and this one here is molecular. But for both of them, I'm still going to go blank plus water is in equilibrium with blank plus OH minus. So I'm going to do this twice, once for each of them. Now, NH3 really is probably the only molecular base we come across this year. There are lots of molecular bases. It's just probably the most common one you would really kind of ever see. Ammonia is used in a lot of different things, especially cleaners. So I'm going to start with the ionic one because I think that's the trickiest one. I'm not writing the whole thing in there. I am not writing NaCN. NaCN, when it's aqueated, does not exist together. NaCN is really Na plus aqueous, and then we have Cn minus aqueous. Now, I don't care about the Na plus. It is not an acid, it's not a base, it's neutral, and really it's a spectator ion, and so those ones are always going to be removed. So you'll notice a lot of times when you have an ionic compound, which is a base, it'll be attached to sodium, lithium, potassium because they're extremely high solubility and they're also neutral. What I really care about is just the Cn minus. So I'm going to put that in here. This is Cn minus. Now the reason why Cn minus can act like a base is because it's negative, it can accept a proton, which is positive. They're actually attracted to one another. So again, a hydrogen is donated from the water. Now this only happens some of the time because this is a weak base. So what does that make my Cn look like? Well, the Cn has gained an H, so now it's HCN. And it's also gained a positive. So this positive cancels out that negative. So I go from being negative to just no charge. So Cn minus to HCN. When I have NH3 aqueous, the same thing's going to happen in terms of water is going to donate that proton like this. So what does NH3 now look like? Well, NH3 has gained an H, so now it's NH4, and it's also gained a positive. So over here, it had no charge. It was a charge of 0. So over here, it needs to gain a charge, which is positive. So this becomes NH4 plus. In both examples, the original species, when it converted over to its conjugate acid, because this is the acid that it's formed from the base, is going to be one more positive. So this is -1 to 0. And 0 to +1. So when I look at a base and I want to know, hey, is this thing monoprotic or diprotic, etc., I essentially am looking for kind of one of three things, okay? So I'm looking for something that has just one hydroxide in it and it's attached to lithium, potassium, sodium. That's going to be a strong monoprotic base. Or I'm looking for an anion that has a 1 negative charge. Because it has a 1 negative charge, it can only accept 1 proton. Or I'm looking for NH3, just because that's essentially only the molecular base that we come across at this point. So let's move on to polyprotic bases then. So there's two types, just like there's two types of polyprotic acids. So you have a diprotic, which of course would have the ability to create 2 hydroxides, and triprotic would have the ability to create 3. So when I look at a compound, what I'm looking for is one of two things. Something with 2 hydroxide ions on the end of it, like strontium hydroxide, or something with a 2 negative charge. Now, right now, I don't see anything with a 2 negative charge. But remember, sodium sulfite, this is sulfite, is really Na plus, and it's SO3 2-. This sodium is a spectator. It does not matter. I don't care about it. It's not going to be in my net reaction. It has to be the SO3 2-. So in general, I'm looking for something that has a 2 negative charge, or I'm looking for something that has 2 hydroxide ions, and realistically, there's only 2 that are highly soluble that have 2 hydroxides, which is strontium hydroxide and barium hydroxide. However, I don't really use them too often in examples, just due to the fact that our data book solubility table says that they are insoluble, even though they are actually quite soluble. So I'm just going to do the strontium hydroxide up here because it doesn't take very long. So it would be OH2 solid, or I can even make that aqueous. This turns into strontium 2 plus aqueous plus 2 hydroxide ions aqueous. So it is diprotic because it dissociates to produce 2 hydroxide ions for every 1 strontium hydroxide. So there's the dissociation. The reaction though will be with the sulfite. So again, I just do blank plus water. Because this is a weak base, equilibrium arrows, blank plus OH minus, and I know it's OH minus because it's a base. Here's my second step, blank plus water is in equilibrium with blank plus hydroxide. Now I just have to fill in those blanks. So starting with SO3 2 minus, aqueous, this hydrogen from water would be donated here. So what does SO3 2 minus look like now? Well, it's going to look like HSO3. And because it gained a positive, it's going to have 1 less negative, so it's just going to be -1 now, aqueous. Then I take that, I bring it down, HSO3 minus, aqueous. Hydrogen is donated. What does it look like now? Well, now it's H2, and then it's SO3. And of course, it has 1 less minus, so now it's just neutrally charged. And the same thing applies. Each time this step happens, it ionizes less and less. So the second step happens even less than the first one. Off to triprotic. So by this time, I think we're probably getting into the hang of it. What we're looking for here is something with a 3 negative charge. And I don't have a highly soluble hydroxide compound that has a 3 on it, something like aluminum hydroxide, AlOH3. It's not highly soluble, and so I wouldn't include it here. So again, when I look at K3PO4, I understand that this is K plus and PO4 3 minus. Well, that 3 minus there is going to make it triprotic. And so I can write out those 3 steps. I can write out blank plus water is in equilibrium with blank plus hydroxide, and I will do that 3 times. Now, by the time you get to the third step, this doesn't really happen, but we're just drawing out hypothetically, how it reacts and why is it triprotic. If I put PO4 3 minus with a strong acid in a ratio that is 3 to 1, so something like 3 HCl's for every 1 PO4 3 minus, it would strip or it would donate all 3 of its hydrogens to it. Okay, so last one, let's get in the rhythm here. We start with our PO4 3 minus. It's got to gain an H, HPO4, 1 less negative, so it's 2 minus. HPO4 2 minus, it gains a hydrogen. Now you're H2PO4 minus, and now it gains another hydrogen. So H2PO4 minus plus another hydrogen, you're at H3PO4. And again, this last one essentially probably wouldn't even happen. So just to finish it off, I want to do something similar to what I did for the acids, which is to use my page to help me understand what's the product that's going to be made when we ionize, if it's a base. Now, if we're doing that, we're really going to have to read this page backwards from right to left. So I'm going to use the example of the ammonia. So if I was like, hey, what is that reaction going to look like with water? Well, this would be my blank and my blank, but I would start by going blank plus water, and then this would be in equilibrium with blank NH4 plus OH minus. But please remember, we would be writing this reaction the opposite way. We're writing it out from right to left rather than left to right, because we need to start with the base, and the bases are in this column here. And so that's how that would be done. The other thing I just want to point out is, hey, if I was looking at something, how do I know if it's triprotic or monoprotic? I just look at the charges here. So triprotic 3, diprotic, diprotic, monoprotic, monoprotic, diprotic, diprotic, monoprotic, triprotic, monoprotic. That's how I can figure out whether that base is going to be mono or di, is just looking at the charge. And then I've asked you to memorize this one molecule, NH3, and of course it's monoprotic. I hope you have enjoyed this lesson of You Got Hope Chemistry. See you next time.